Okay, I wanted to show you a couple of things about tables. I don't know if I did put this in, give this to over to the Google Drive or not, but I'll make it available for you. This is a nice knot table that is just one PDF that you could use. And let's leave it up and illustrate something about it. We did this before, but we could do it again. If you wanted to find out about the coloring of some small knot, you can just walk over to the table and take a picture of it, like say it's 7.5. Let's look at 7.5 there on the table. So 7.5 goes like this, and like that, and then like that. Oh, did I misdraw it? I misdrew it. Let me do it again. I'm not doing a good job. Let's start again. Oh, I forgot. There's a way to, oh, that's it. That's fine. Yes. Okay. So I wanted to get the diagram for 7.5. So I'm just copying it without worrying about over and under. And then 7.5 happens to be alternating. And the way it's drawn here, it goes over on the left. So we could draw it again. It goes over and then it goes under, and then it goes over, and then it goes under, and then it goes over, and then it goes under, and then it goes over and under. And it's going to go over at this point, and then under, and I need one more over, and one more under, apparently. Or let's just draw this way and fix it, sorry. So I need to fix this and this, and it's going to alternate. So it goes under and then over and then over and then under. And then, oh, that's where we made a mistake. I'm illustrating to you that it's clumsy to make copies of drawings. Okay, under, over, under, over, and under. And there's 7.5. All right. But then we wanted to find out whether we could color it. And for small knots, you can usually find a modulus for them without solving the system of equations by just doing an attempt at coloring. And let's do that here just because that's kind of fun to see whether you can do it, but you don't get the complete story necessarily. So 2 times, so remember that our method here is A and B, and this is 2B minus A. Or in other words, that the sum of C and B, C and A is twice B. So 2 times 1 minus 0 is 2. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 2 is 4. 2 times 4 is 8 minus 1 is 7. So we're succeeding in propagating the colors all over the place. 2 times 7 is 14 minus 4 is 10. And 2 times 10 minus 3 is 17. Right, that's correct. So we need to be in Z mod 17 in order for this to work. So there are a lot more colors than there are colors on the knot, where we have 17 possible colors, of which we've only used a few. And does this all work? Just double check it. 2 and 4 is twice 3, 2 and 0 is twice 1, 1 and 7 is twice 4, 10 and 4 is 14, which is twice 7, and 17 and 3 is twice 10, but also 3 and 0 is equal to twice 10, because 2 times 10 is 20, which is congruent to 3 mod 17. So there's an example of this kind of computation, right? If we were to have written down the system of equations for this, we would probably find in this case that indeed the determinant is 17, my guess. But you won't necessarily get the determinant. You would, if you do this method, you'll get to a divisor of the determinant, but you won't necessarily get the determinant. So maybe it would be fun actually to take this one and write the system of equations down and see what it's like. But how much fun is it going to be? 1, 2, 3, 4, 5, 6, 7 crossings. So there are going to be 7 equations there. And a matrix that's 6 by 6 by the time you remove 1 column and 1 row. So I say it's a good exercise in this case, and I'm going to show you another example of it. But exercise, write the system of equations. And find K is 7, 5, and find the determinant of the knot K. Okay? You can do that yourself, just the way I was describing it, and I'm going to show you another example. But I want to show you something else as long as we have a knot up in front of us, and that is the following. That if you look at just the diagram of the knot like this, it's a graph in the plane, of course, and let's draw it again so we can play with it a little bit. Right. These graphs in the plane have a very simple coloring theorem as far as their regions are concerned. You can two-color them in such a way that if 2 regions are adjacent, they have different colors, like a checkerboard. And to see that, give it a try. Just try coloring it. So I try shading it with 2 colors, black and white from the board. And you see, it's working. I don't have any contradictions here. And I have 2-colored the diagram. 2-colored, 2 face-colored diagram. It can always be done. That's a theorem, of course. But before proving it, I think you should give it a try. All you have to do to give it a try is to doodle. Just draw yourself a diagram, some diagram, and then shade it in 2 colors so that if 2 regions are joined, they have different colors. And find out that it's always working. And then ask yourself, why is it always working? And that's another exercise. Why? Okay. I'll tell you on Wednesday, right? My why. But I think I know 2 or 3 proofs of this myself. And if you look at it, you probably will come up with again another proof that you can always 2-color this. Much easier than the 4-color theorem, believe me. Very easy, but a nice exercise to understand that this can be done. But now, given that that can be done, you can do a little more graphical thing. Let me see now. Let's get another color. How about green? And I'm going to put a vertex in each of the shaded regions like that. And then I'm going to put an edge for a graph if two regions are meeting along a vertex. Yes. And I get a graph. So in this case, my graph, let me copy it, has these two vertices here. And then it's got this big vertex here with a lot of edges coming off of it, and a vertex over here on the right. And these guys are both connected down to those vertices. These vertices are connected to each other twice, multiply. It's a multi-graph. And there's a vertex down here, and it's connected up to these two. And I will call this the graph of the diagram, okay? So this is the diagram. I'm not worrying about over and under crossings. That's the graph of the diagram. And so you see that if I have a diagram of a knot or a link, I can always produce, because of this theorem of two coloring, I can always produce a graph for it. And it's just a planar graph. It's not anything special. It has different degrees of vertices dependent. It's got a degree 2 vertex, it's got a degree 2 vertex, here it's got a degree 4 vertex, and so on. Just a graph in the plane. And this goes back and forth. If you have a graph in the plane, you can construct a corresponding diagram for a possible knot or link. It goes back and forth. The way it goes backward is as follows. Let's draw this again, and I will do the backwards process on it. On each edge, put a little X. That's going to be the crossing. Okay? If you look back over here, you see there was a little X from the knot diagram at every edge, right? Look at an edge. And right in the middle of the edge, you see the knot diagram crossing through it, right? Because that's the way we made it. We made sure that an edge corresponded to a crossing between two regions. So I put a little X there, and now I'm going to fill in the diagram. And the way I'm going to fill in the diagram is I have a face of the graph, and I start walking around the boundary of the face. And I connect to the first part of the X that I meet. And of course, I'm creating cycles in a graph, but those cycles are living in the plane. And each of those cycles corresponds to the cycle in the original graph that is the face of that graph. And I just keep filling them in that way. Now, you know what to do because you start walking along the edge toward the corner. It's always well defined. You have somewhere, a corner, and you have an X here, and you have an X here, and you start with the angle that's pointing toward that corner, and you walk toward the corner, and then you walk away from the corner, and you take the part of the X that's pointing toward it on that side, and that's what you fill in right there. So it's always the same, that uniform method of filling it in, and you fill it in. So of course you should actually sit down and do this to see that, to convince yourself that in action, all of this works out fine and that it's consistent with your practice of making drawings as well as abstractly. But there you are, and we've reconstructed the knot diagram from the graph. So you can go back and forth between graphs and knot diagrams, and this is quite a pleasant occupation. Let me show you what I mean. Suppose that I decide to take some graph, like this one, for example, and I wonder, well, what knot diagram will that be? Of course, you can choose crossings if you want to as well. So you could, for example, decide to uniformly choose a certain type of crossing at each one of these, and then you would produce a weave. Okay, but I'm just talking about getting to the knot diagram. So let's get another color back. How about this color? And I want to make the corresponding diagram. So I put an X at each one of the edges. And then I make my connections. Of course, I could make my connections by just walking along. Then I would be going inside and outside, and I'd have to keep track. But I can do it that way as well if I want to. This. Seem to be done, and we have a little something to erase here. So there's my diagram of a knot. And then when you get the dot diagram, the artist in you will probably want to redraw it and make it look better. So it's a bit surprising. You draw a graph and then what kind of a knot diagram am I going to get out of it? And you can't quite tell because you need to see the whole. And so you go ahead and actually do it and you find yourself with an interesting knot diagram. And mathematically, that means that we have the diagram and we have the graph of the diagram. And shouldn't there be topological information about the knot in the graph of the diagram? Well, sometimes there is. So it's a good thing to be able to go back and forth between one language and the other. The full language of graphs, in this sense, planar graphs, and the language of the knot diagrams. I'm going to quote a theorem for you. And we'll look at it in a simpler case than this, and then we'll look at it in this case. So here's the theorem, which I might be able to sketch at a later point, but here's the theorem. Now remember that the determinant of a knot is a positive number or zero. It's the absolute value of the determinant of the matrix for coloring, right? That's our definition. The matrix for coloring is the n-1 by n-1 matrix when there are n crossings. That we've talked about before quite a bit, right? You form the matrix for doing the coloring, and you knock out a row and a column, and you take the determinant of that, and that's the determinant of the knot. It should be the largest usable modulus that you can do for the knot, and this may be the determinant. We'll find out in a minute by a little looking up. I'm going to find out for you. You can do the exercise, but I'm going to find out for you and show you how to get information from the internet about determinants and things. But here's the theorem. The theorem is that the determinant of a knot or link K is equal to the number, this is my shorthand for number, of maximal trees in the graph of the knot. if anything looked non-obvious, this theorem looks non-obvious to me anyway. But of course, after you know how to prove it, it is not quite so non-obvious. Do you believe that? Then in other words, if you were to take this knot here, then the claim is that we could look at its graph. Oh, we already have its graph here. And you would want to count, I'll make the graph a little more visible. We would want to count how many trees there are in this graph. Now that's a little too big to do. So let's illustrate this theorem with a couple of examples that we already know. I'm not going to prove the theorem today, I'm just telling you the theorem, but we can easily do a couple of examples to see if this is true. Let's go back to the trefoil knot. Here's the shading, and that tells us that the graph of the trefoil knot is just a triangle. G of the trefoil is just a triangle graph, and maximal trees in G is equal to the set consisting of remove one edge, right? 3. So 3 is equal to the number of maximal trees in G. 3. But we know the determinant of the trefoil knot is 3. So that's an example of the theorem. Try another one. Let's see. I'll do an relation. We can do the figure 8 knot. The trefoil and the figure 8 knot are the two that we really know those examples really well. So what happens with figure 8 knot? Oh, I misstated my theorem, of course. You must have been skeptical at this point because I didn't give you a hypothesis. And K could be an unknot, right? An unknot could have a perfectly nice graph. You could have switched to crossing in this trefoil knot, and the graph of the trefoil would still be the triangle, right? So there must be a hypothesis in this theorem. And the hypothesis is K alternate. And an alternating knot means that it goes, as you walk along, it goes under and then over and under and over and under and over in sequence like that. All right, you never have two overcrossings in the diagram. You never have two undercrossings in the diagram. It alternates. Alternate weaves are tight weaves, and because they're so tight, they end up being related directly to the underlying graph. And this is an example of a theorem of how they're related. So alternating. And then the figure 8 knot, that's certainly alternating. And if we were to, if we were to shade it and obtain a graph for it. And this is not too complicated a graph. Here's the graph of the figure 8 knot. And the claim is then that how many, given what you know, how many maximal trees are there in this graph? Well, you know the determinant of the figure 8 knot is 5. So there should be 5 trees. Can you see the 5 trees? Well, you sure you can, right? Let's draw some trees. Here's a tree using both of these. If I only use one of these, then I could use one of these. But I could also use the other one. and then one of these. And that's 5. And there they are. They're the 5 trees that are the maximal trees in the graph. Now, I didn't say out loud the definition of maximal tree, but what could it mean other than what I'm illustrating? A maximal tree is a tree in the graph that uses every vertex in the graph, okay? It's the largest possible tree that you can draw in the graph, okay? So every graph has maximal trees, and it is an interesting graph theory question. How many maximal trees are there in this graph? How does it grow in terms of the structure of the graph and so on? And how do you enumerate all the maximal trees? Well, if I gave you a complicated graph like that one, like this one, this is the one we're looking at the moment, this nice graph here. How many trees do you think this has? Let's call this graph H. The number of maximal trees in H is equal to 45, I claim, in this case. Quite a large number of trees, okay? You could enumerate them all. And if you wanted to enumerate all the trees in even a medium-sized graph like that, you'd have to find a systematic method, right? Does anybody happen to know a systematic method for enumerating the trees in a graph? Okay, in a little bit, I'm going to show you a nice systematic method that I like, but we'll come to that. This is just a very interesting theorem that it turns out that this determinant, which looked like a very algebraic thing having to do with our funny rules about coloring, is a global property of the underlying graph. It's the number of maximal trees in the graph when you have an alternating knot. So it's something to think about. Why did that happen? Now I want to show you about looking things up on the internet. If you go to the internet and you write the name of a mathematician friend of mine named Dror Barnatan. He's in Toronto. This is Dror. And he's from Israel originally. And he has a web page, which you'll get to right here. Okay. And I recommend his web page because he has many interesting things on his web page. You can have some fun looking around on it. He works mostly in knot theory. Among other things I noticed when I looked up his web page the other day is I saw an entry that says, I still don't understand Vogel's construction. And I got to wondering, well, what is that about? And I found that he had written a whole list of things that he feels like he doesn't understand. He's kind of bragging, I don't understand this and I don't understand that, meaning I understand a little about this, but I don't really understand it, just like everybody else. And so all the things that he is listing here that he doesn't understand, like I don't really understand general relativity, they're all things you would like to understand. You can have fun reading his list and saying, well, gee, I really would like to understand that too. And some of it's technical, having to do with knot theory. You go to another part called the Knot Atlas and click on it. And you will see that there's quite a bit about tables of knots, various tables of knots. The one I recommend to you first, you can do other things, is the Rolfson table of knots with up to 10 crossings. Click on that. You get a nice table, and each of these is a clickable knot, okay? If you click on one of these knots, you will get a lot more information about that knot, okay? So if we were to go to, we got interested, we started calculating a little about 7,5. So we could go on his table and find 7,5, there it is, and click on it. I have to click on the number. There. And you get a picture of 7,5. You get some lore about it, like other kinds of pictures. And incidentally, this is another kind of picture that turns out to be remarkably important. You might think, oh, just decorative. You could always draw a knot so that it's made of vertical and horizontal lines. And in fact, you can always draw knots so that the vertical lines are always over. Actually, that's obvious, isn't it? If you could draw it with vertical lines and you had one where where it was under, the vertical line was under, you could just redraw it by turning it a bit and it would be over. You just make a more complicated diagram. But you can draw any knot made out of vertical and horizontal lines. And it turns out that that way of representing knot diagrams is very important theoretically. I won't say more, but we can say more about that. So when you go to his tables, you'll see some various drawings. And then you will see what the computer tells you about it, the Gauss code, grades associated with it, and then polynomial invariance of the knot. And if you keep walking on down, you should find the determinant indicated. Determinant, there it is, 17. Determinant and signature. So you see here, he has listed that the determinant is 17. So when you do your exercise, you should find 17 when you do it using those equations and take that determinant. I was guessing that my rough calculation was actually the determinant. Of course, you have to do a lot more work to get the determinant. You have to write down the matrix and take its determinant. But then the other number is called the signature, and we'll talk about the signature at some point. The signature is another very useful invariant of the knot. When I say invariant, of course, I mean something which doesn't change when you do the randomizer. So this is Rohr's webpage, and I got interested in fooling around with another knot, which is 818. So let's go back and get 818 out of here. There's a 818. 818 is the very one that we just constructed from a graph, right? There it is. That's 818, 4 in the middle and triangles and so on. And it's been made alternating. 818 is an alternating knot. And this one turns out to be often used as an emblem in various places. So in his lore about 818, you will see quite a lot of pictures, not the least of which is that it's the logo of the International Guild of Knot Tiers, or not knot theorists. They are people who are interested in the art of tying knots and using them practically, and they have a guild, and they're English mostly. So you see other things like putting the knot on the surface of a sphere and decorating uniforms with an emblem and so on and so on. And we would like to know what is the determinant of that knot. So we're going to go down through the tables to get to the determinant, and it's 45. It turns out it has signature 0, 45, and that's why I say that the number of trees in this graph should be 45 by my theorem over here. Okay. Okay. Now, what about finding the determinant of this knot? Let me show you how it might look if you were going to do this with a computer. Now, I must apologize that I didn't make a very good photo of my notebook, but I think you can see what I'm doing anyway, even though it's a bit fuzzy. All I did was I labeled the arcs, A, B, C, D, E, F, G, H, and that's a name, B, C, D, and the crossings 1, 2, 3, 4 out through 8. And then I wrote the equation for each of these in my matrix, right? 2A is equal to D plus E is what happened here. You had at number one, you had, 2G equals D plus E, 2G equals D plus E, right? So I wrote down the system of equations. I don't bother to write the equations, I just write the matrix after all. Why should I bother writing the equation? Yeah, and then I'm going to take the determinant of this part here. And for that, I'm going to use my computer because I'm lazy. And that's not a whole lot of work given my computer. I just write down the matrix. This is the 7x7 matrix. And I tell the computer to give me the matrix form of that. This is the way you input a matrix, rows. And then you tell the matrix to show you the matrix form and calculate its determinant. And then I'm going to do the coloring calculation. But so far, I just want to go to get the matrix. So there's my matrix, right? It's going to be a matrix that looks like that, 2's and -1's, because I'm writing each one as twice the overcrossing line is the sum of the two undercrossing lines, right? You can write that down. And then you take the determinant and it's 45. So there we are. The determinant is -45, it turns out, but the absolute value is 45. And then what's this other thing? Well, remember what we said, right? We said that if you had M, the matrix, then if you multiplied it by what I call the adjoint or adjacent matrix, then we would get the determinant of M multiplied by the identity matrix. And the adjacent matrix, I say adjacent because someone points out to me that while sometimes people call it the adjoint matrix, other times people talk about adjoints in terms of another part of linear algebra, and it's confusing. So it's called two things, and we'll call it the adjacent matrix. The adjacent matrix is, in fact, equal to the determinant of M times the inverse of the matrix. And that's good for the computer, but it has integer entries when M does. When M has integer entries, the determinant of M times M inverse also has integer entries. And there is a specific formula for the adjacent matrix that is given in terms of minors of the original determinant. You can look it up in a linear algebra book, but if you're using a program like I am here, then I just say to the program, give me the matrix of the adjacent determinant of M times the inverse of M. And the reason I'm interested in the adjacent is because you see that if I work to modulo the determinant, then M times the adjacent matrix would be equal to the zero matrix mod the determinant of the knot. So that says that every column of the adjacent matrix is a coloring solution, right? Take a column, M times that column will be equal to 0, but M times that column is the equations applied to it. So all the equations applied to it will be zeroing out, and we will have a coloring of the knot. So then I have asked the computer to do all that work for me instantly, and it gives me the adjacent matrix here. And now I just look at, say, the first column, and it says 24, 6, 12, 15, 9, 36, 12. We're working mod 45. This is B, C, D, E, F, G, H. So I go back to my knot, and I say, okay, 36, 12, 0, 24, 6, 12, and so on. And there it is. And we're working modulo 45. and I claim that that's a coloring of this not modulo 45, you can check. For example, 12 plus 9 is 21. And I'm sorry, 12 plus 6 is 18. And 2 times 9 is 18. You got to choose the numbers right to get the arithmetic to work right. Do another one. 12 and the side-by-side numbers are 9 and 15. Now 9 and 15 is equal to 24, and 2 times 12 is 24. So that's working. Somewhere we're probably going to have to use the modulus, probably here because the numbers are getting larger. 36 and 12 is 48. No, 2 times 24 is 48. Somewhere surely the modulus comes in. How about 12 and 15? 12 and 15 is 27. Oh, but 2 times 36 is, no, 36 should be twice 27. But what is twice? No, I'm getting myself confused. A plus B is twice what's going across is supposed to be. You too could get confused. Let's say what we're saying, right? You have A and C and B, and 2B is equal to A plus C. That's my way of thinking about that, right? So if we're over here at 36, then twice 36 should be equal to 12 plus 15. Now 12 plus 15 is 27. And 2 times 36 is equal to 72, which is equal to 45 plus 27. Aha, okay. Where we use the modulus. Okay, right? So it is true that twice 36 is congruent to 27 mod 45. So this guy is colored mod 45. But the beautiful thing is, if you're willing to use the computer, it feels beautiful, that you can calculate this adjective matrix and then there they are. There's a whole list of colorings and you've solved they've actually solved all the coloring problems that there are up to linear combination. Any other coloring will be, with 0 on that one edge, will be a linear combination of the columns of the adjective matrix. So this lets you go quite deeply into what the colorings of a knot are by doing a little algebra. And if you have a computer program, you can investigate that. Okay. So that's the story about that. And then let's see how our time is running. This not being the only thing we wanted to talk about today. Did I bring? Yeah, I did. Okay, we're good. Let's go to the next board. And I wanted to digress into the question of how do you enumerate the trees in a graph? How do you enumerate the trees in the graph? And there's an algorithm that I like very much. This is called the Wang algorithm. For enumerating, I'll abbreviate it for, well, I won't abbreviate. For enumerating maximal trees in a graph. Let me illustrate the algorithm on an example while we do it in general. Let's say this is our graph. 1, label the edges. 2, 2 for each vertex, for each node, write the sum of the edges incident to the node. Right? So I would have A plus B plus E from number 1. I would have B plus C from number 2. I would have A plus D from number 3. And I would have C plus D from number 4. Okay? Great. Regard the edges as generating an algebra algebra where A squared equals 0 for any edge A. Let's call this algebra A of the graph G. And 2x equals 0 for any x in the algebra. So if you found yourself, for example, AB, and you had somewhere else AB, that would be 0. Right? 4, right? Product of all but one of the node sum. And reduce it by 3. The result is a sum of all the trees. Try it out on something simple and then we'll try it out on that. So example A would be this little triangle graph, and we label the edges A, B, and C. And I'm going to form A plus B times B plus C. Right? I'm not using A plus C. This is the product of all but one of the node sums. Doesn't matter which one you eliminate. Eliminate one. So I have A plus B times B plus C. And I multiply out and I get AB plus AC plus B squared plus BC. B squared is 0. So I get AB plus AC plus BC. And then I go back over here and I see this is AB and AC, this one, and BC is this one. And we have just enumerated all the trees in the graph. This is very easy to write a computer program to do this, you see, and then you can do it also by hand for relatively small exam. So, let's try it out on our other example here, over here. Now, over here, it probably would be a good idea to keep it simple and use 2, 3, and 4, since that one, wait, 4's got a mistake. C plus D plus E, right? So I'm going to have 1 with 3 and 2 with 2, or 2 3's and 1 2. But I'll take, so I might as well take 2, 3, 4, that's okay. So then I would have B plus C times A plus D times C plus D plus E. Okay. Make sure C, D, E, and A plus D and B plus C. AED is the one we left out. AED is the one we left out. Okay. So let's multiply this now. So I get AB, I'll try to put them in alphabetical order. AB plus BD plus AC plus AD plus CD times C plus D plus E. Yep. AB, BD, AC, CD. Okay. And now I multiply this out, I get ABC, AB, I'm doing C, plus BCD, plus AC squared, that's 0, and plus ADD. Then D, I get ABD, BD squared, 0, ACD, and CD squared. That's 0. And then multiplying by E, I get ABE plus BDE plus ACE plus CE. So altogether, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, unless there's any repetitions. Any repetitions here? Don't think so. But I had the feeling it was really 8, not 9, so I might have made a mistake. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. That could be right. For example, CDE, C, D, and E, that's this little efflorescence here. And there are things like A, E, C, or C, or B, E, D, and so on. You can check. Check it again and see if I got it right. And you could compare it with the corresponding determinant if you like, right? Because what we had there is to be compared with what? It's to be compared with the corresponding alternating knot. Or length. So it's a link. And you can go and look at that and work out the determinant and so on. So there's something to do there. You can have some fun, right? But this Wang algorithm is a very nice algorithm. And you might also try it out on some things and see that it really is working. It involves a little bit of algebra there, but that's all. And if you ask yourself, why is it working? Then you have a nice theoretical question to ponder. Why does it work? Can you prove that this algorithm really always works? It does. Just to finish that bit, let me show you what my computer program looks like for doing that algorithm. It looks like this. That I use, these are just possible vertices. In the computer, I have a vertex with 2 things coming out of it. I have a vertex with 4 things coming out of it. I have a vertex with 5 things coming out of it. I don't know why I didn't put a 3. Oh, I did. 1, 2, 3, 4, and 5, so that I can write symbolically, this is some vertex, A, B, F, like that. And then it will turn it into the sum of the vertex names. And the vertex names are X bracket A, X bracket B, the edge names are X bracket A, X bracket B, so on. So, so I've told the computer how to turn each vertex, that being the name of the vertex, into a sum of labels. And then I have that a label multiplied by itself is 0. And then I also have another rule which will take a label and turn it into a 1, because at the very end of the process, if you turned every label into a 1 and added these numbers up, not mod anything, then you would get the number of trees. And then I tell it to expand the product, and I get the different answers as a result. So you see, I'm inputting the product. What I input into it is already the product. And then the computer just goes ahead and expands the individual entries in the product into the sums, and then multiply them and applies the rules, and everything works out. Okay. And for example, here's the example that we were working with before. This is the graph that had 45 trees, and these are the vertices that I'm interested in: A plus B plus C, C plus D plus H, and so on. And I gave it those. And asked it to tell me how many trees there were, and it said 45. And I asked it to write out what the trees are, and that's not very pretty to look at. But if you look at the individual products in there, there are the trees, and they've all been enumerated. So it can be done, right? If you use Mathematica, I can share the program with you. Otherwise, you can give it a try on your own. I'm fond of the Wang algorithm, and it amuses me a bit to think that I can start with a knot, get the graph, and then apply this algorithm and find an invariant of the graph. I get the determinant that way if I want to. So let's continue. Let's go back now to rational knots and links. So any questions before I start in this back into a different topic, right? Do you have questions? Okay. What were we doing with rational knots and links? Let's recall from the beginning. We had some basic rationals. This one is 0. This one is 1. This one is -1. There's 2. So on. And we have that there is a fraction corresponding. Now, a rational tangle is made from 0 by adding twists. Horizontally and vertically. So what I mean by that is I could start from 0 and I could, but it's not a good idea for me to add a vertical twist at that point. I could add some horizontal twist. And then I could add some vertical twist. This is not a topological operation. This is a construction operation. I could add a vertical twist. Then I could add a horizontal twist to that. And then I could add a vertical twist to that. And maybe one more horizontal twist to that. Call that my tangle. So that's a typical rational tangle. The only thing is I have drawn this one in an alternating form. It might not be alternating, not necessarily alternating. Oh. I touched it one too many times. Do we know how to bring it back to its standard form? Oh, that's good. Bring the wood. Can you just drag it?
Oh, yes. Thank you.
Oh, good. Thank you.
No
All right,
worries.
now we're back to normal, I hope. A little bit of that one matter too much.
Thank you.
Not necessarily alternating, okay? We're going to think about that in a moment, show some examples. But this one's alternating, and when it's alternating, and this one happens to be positive, see, this was a 3, right? And it's alternating. So, and this one was a 3, and this is a vertical. Now, I really should write it as what it is. So this is 1/3 over here. And this one is a 2, and this one is a 1/3. But really, the numbers are 3, 3, 2, 3, 3, if I'm just thinking about how much twist was going on, right? And we showed last time the following thing, that if you have a tangle and you have a twist of type n this way, then this is going to be t plus n if t is the fraction of t. And on the other hand, if you had a tangle and you had a twist this way, which I will write n, looks like this, still n, positive, like that, then this will be 1 divided by n plus 1 over t. That's what we found, remember? When we used our rules. And our rules were that our rules were this one, and the other rule that we used was that if you rotated the tangle by 90 degrees, then this will be minus 1 over t. So we really had only two rules, the minus 1 over t rule and this rule, but then together you got this because you could rotate that by 90 degrees, you see, and then you would get minus 1 over whatever it is, and you could work it out, and we worked it out, and that's how it behaved. And I won't go through it again, but that means that this tangle here is 3 plus, we can read it out, 3 plus 1 over 3 plus 1 over, and now we're looking at this guy, and this guy is 2 plus 1 over 3 plus 1 over 3. So we can actually read out what the fraction of a rational tangle is as a continued fraction. And that's what we were doing last time. I did simpler examples. This is a slightly complicated example, but it's okay. And we might as well do the work. And find out the value of this. So if you'll pardon me, I'm going to do a little more erasure on the diagram because I prefer, even though this is really 1/3, I would rather just label it 3. And in fact, I'm not going to label it anything because we can all look at them and count. And then we can try the other method that I showed you about coloring. But let's do the calculation here. So I haven't done it. Hopefully all the arithmetic is going to work out. So this is 3 plus 1 over 3 plus 1 over 2 plus, now 3 divided by 3 1/3 is 1 divided by 3 1/3 is 3 divided by 10. Please yell at me if I make a mistake in my arithmetic. I'm looking at that last part, 3 divided by 10. Okay, then we get 3 plus 1 divided by 3 plus multiplied by 10, and you get 10 over 23. Agreed? 10 over 20 plus 3, yes. And then that's equal to 3 plus 23 divided by 79. Right? 3 times 23, 69, and 10 is 79. And then that's equal to 3 times 79, which is 237 plus 23 divided by 79, which is 260 divided by 79. So I hope that is correct. 210 and 27 is 237. Yeah, okay. So 260 divided by 79. But I showed you this other method, and the other method was that you color the tangle, and then you look at the end colorings R, S, P, Q, and you look at R minus S divided by S minus, R minus S divided by P minus S, if I'm going to do it in that direction. And that will turn out to be the tangle of the fraction. And we did this with a small example. And maybe it's a little daunting to try doing it with a large example right now because we'd have to do a lot of arithmetic, right? So here's another exercise for you. You can try it out. You don't have to do this one, but try it out on some example where what you do to try it out is, I like to call this one 0 and that one 1, and then continue on coloring it, right? 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 2 is 4. And 3 comes down here. And then you keep on going and propagated coloring for the entire rational tangle like that. And then the fraction, this is equal to fraction of the tangle. So what is it that you would like to prove about tangle fractions if you were going to do this? You would like to prove that the tangle fraction obtained by adding a twist on the right adds an n. And that the tangle fraction that you get if you turned it by 90 degrees would be minus 1 over n. So let's do one of these and leave the other one also as an exercise for you to do, an exercise which I will do at some point, okay? But let's just consider what would happen if you had a tangle. Maybe we should do it with a real one. Let's do it with a real one. I'll go on to another board. Let's take a real one that isn't too large, like this one. Okay, and we'll do it 0 and 1, and then 2. 2 times 2 is 4 minus 1 is 3, and 2 times 3, 6 minus 2 is 4, and then here's a 0 and here's a 3, and this would be a minus 3 then coming down here, and this would be a minus 6. And then I like to go this distance in that one. So 4 minus 1 divided by 4 minus 3 is equal to 3, 7. So that guy is 3, 7. And if you did it the other way, you would have said 1 divided by 2 plus 1 over 3, right? 1 divided by 2 plus 1 over 3, and that's equal to 3 divided by 7, check, right? So, works. Now, what if we added a twist on the right? So I'll copy it. And I'll add a twist on the right. One, two, three, 4 on the right. And we'll go through the coloring process again. 0, 1, 2, 3, 4. And 3, and minus 3, and minus 3, and minus 6. And you see that I can think of doing just that. When I add the extra twist, I just take the colors on the right and feed them into the twist. So you can see how you would prove it in general. I'm just doing it on an example. So 2 times 4 minus 3 is 8, and 3 is 11. And 2 times 11 is 22, minus 4 is 18. And 2 times 18 is 36, minus 11 is 25. And 2 times 25 is 50, minus 18 is 40, minus 8 is 32. So this is a 1. So I'm getting 31 divided by 6. which is equal to 4 times 6, 5 times 6. 1, 2, 3, 4. Must be arithmetic error here. All good up to this point. We must have made an error here. 2 times 4 is 8 and 3 is 11. 2 times 11 is 22 minus 4 is 18. That's okay. 2 times 18 is 36. Oh, 36. Yeah, minus 11 is 25. 2 times 25 is 50 minus 18. Minus 18 is 40, minus 8 is 32, and there's 25. It doesn't look like there's a mistake. And I'm getting 32 minus 1 is 31. Oh, that's a 5. Right? 25. Oh, what am I doing? It's a 7. All right, I can't do arithmetic today. 32 minus 25 is 7. There. All right. Now we're okay. 31 over 7. But what happened? 7 goes into 31 4 times with a remainder of 3. And there you are, 4 plus 3 7. So that's how it goes in practice. And you see that the way it goes in practice is the way it's going to go in general. So you could write down a proof in general and get that the fraction of the tangle plus n is equal to the fraction of the tangle plus n. Okay? And you should try the rotation by 90 degrees yourself. Now, what is it that we're finding out about here? It's really actually quite interesting. When you do a Reidemeister move on the inside, it won't change this because coloring doesn't get changed by Reidemeister moves. So these are actually, so this fraction is actually an invariant of the tangle. It doesn't matter what you did to the tangle, you would get the same fraction. Good. And there are other examples that we can try, but I want to point out something even with this example. You will notice that 4 would be equal to minus 3. Suppose 4 is equal to minus 3. Well, that says we're in Z mod 7, right? And 1 equal to minus 6 says that we're in Z mod 7. There is a fact about the coloring, which is that the colorings have the property that if you've colored them, then you will find, as you can also prove, that R minus S will be equal to Q minus B. And R minus Q will be equal to S minus B. And that means that we get colorings in Z mod R minus S or closing it up like that, and colorings for Z mod P minus Q or S, which one do I R minus S, the other one would be R minus Q for closing it up the other way. You can close up the tangle. This is called the numerator of the tangle, and this is called the denominator of the tangle. We can get a knot or a link by closing it up in that way. So for example, here, for example, here, if we decided to close it this way, this is t, this is the denominator of t, and here we need z mod 7. Then we actually are looking at a coloring that works, Z mod 7, because it works fine all over the interior. And the only extra modulus criterion is that 7, 1 should be equal to -6, -3 should be equal to 4. Same criterion left and right. So you get from coloring the tangles the colors of these so-called rational knots that are obtained by closing the tangles. And if you did it this way, we'd be Z mod 7. And if you did it the other way, you'd be in Z mod 3, right? 4 minus 1 is 3. And in fact, you can see that you're getting a fancy trefoil when you close it the other way, this one, because the twist on the bottom unfurls. You would be getting trefoil twist, and then another little 2 twist, and you decided to close it on the bottom. And this will be colored in Z mod 3 by our general argument, but of course this is equivalent to a trefoil knot. So it's not a surprise that it's being colored in Z mod 3. So actually, I think, and I'll have to see whether I know how to prove that when you do this with a rational tangle in at least standard alternating form, you actually are getting the determinant of the resulting knot or length. Okay, that's not obvious. We'll have to think about it a little bit. But that's an interesting feature of thinking about it this way, is that we get colorings for lots of rational knots. Now, why are rational knots of some interest? Let's see how our time is running. Okay. Well, one reason that rational knots are of some interest is because of DNA. I want to explain in a certain form rational tangles and rational knots. See, suppose you have an unknotted loop like this. Yeah. And so the DNA could start being a long unknotted loop like this. And energetically, the DNA is sitting inside the living molecular environment of the cell, and it can move around. And one of the simplest things that can happen to a long loop like that is that it can twist around like this. And then 2 other strands of it may get near to one another, and they may twist around like this. Now, this is still unknotted, but if you look at what's happening, you see that that it's divided. It can be divided up into a part which is a rational tangle, which is the result of the twisting, and another rational tangle over here, which is undoing the first one. And you can have some fun playing with this with ropes, because you'll see that that's exactly what happens. Now up here, I have a slightly more complicated rational tangle up at the top. See that? And down in the bottom, I have an even more complicated rational tangle down in the bottom. And they're connected. This universe over here is connected by these 4 strands with this other universe over here. So you have 2 rational tangles that are connected up with one another. Now, one of the things that can happen with DNA is that it can undergo recombination. It can happen that 2 of these strands not only twist around one another, but an enzyme comes along, cuts them, and reconnects them. And once that happens, the DNA has been made into a complicated knot if it was already even though unknotted, in some form like this. So the DNA can transform by one small operation from being unknotted to being in a very complicated knot that is in fact described by rational knots, by closures of rational tangles. And as a result, people have discovered that they can use rational tangles and some of the interesting topological information about them to study DNA recombination. And I'll give you some references about that another time. So I wanted to spend the last few minutes, I was hoping more time, but we'll start next time. I wanted to introduce something about linking number and how it's related to another topic that we need. So let's go back to linking number for a moment. Well, so we said we wanted to know the linking number of a link like this, and we said, well, we'll orient one of them. And then we'll orient the other one. And then we'll look at the signs of the crossings. And we'll see, and in this case, we have a plus crossing there, so that'll be plus, and this one is also yep, plus, they're all plus. So if this is A and this is B, then our method told us that the linking number of A with B is equal to 1, 2, 3, 4, 5, 6 divided by 3, linking number 3. And that accorded with our intuition that one curve went around the other one 3 times. Here's another way of thinking about the linking number. What did I do? Under, over, I miscounted one. That should be the same as what I had before. But now I want to think about it a little bit differently. What I want to do is think of a surface that bounds one of them. Maybe I should draw this in a different way so it'll be easier to see. I want to think about a surface bounding one of the components. And the other one comes underneath, pierces this, and comes up over, and it comes underneath, pierces this, comes up over, and then it comes underneath and pierces this, it comes up over and it comes back, and so we end up seeing this, and we had it going this way, right? So it's going along, and it goes through that surface once, then it comes around and it goes through that surface again, and then it goes through that surface again. And this surface is oriented like this. So when you're looking at it, when you're looking at one of those piercings, it looks like this. You have a bit of surface, you have somebody which is coming down through the surface. this. And the surface has a circulation of its own like that. Now, if you put your fingers around the circulation in the surface, the orientation of the surface, and your thumb points in the direction of the piercing arrow, you call it a 1, an intersection number of type 1. If this arrow had been going in the other direction, then your thumb would be pointing against the arrow and you call it -1. But now you see 3 intersection points. And so we can say the following, that if B is equal to the boundary of C, and I use this term for boundary, then we can write that the linking number of A with B is equal to the intersection number of A with C. Now, I hope all that's intuitive to you. We don't need this, so we might draw something in there instead. Think about it for a moment. This is all I'm going to do today to finish. I won't go on to talking about boundaries of other things, but I do want to talk about boundaries of other things and how you can use the concept of boundary very fluidly in thinking about topological problems. But here, instead of counting all these crossings, this is a geometric idea which happens in 3-dimensional space. I have one of the curves is bounding some surface. And then I look at the other curve and see where it's forced to pierce through that surface. And I count how many times it does that. And of course, it might pierce through the surface and come right back, in which case you would find it going plus minus, and you wouldn't count it, right? But some things are irreducibly happening here. It goes around through and then it has to go around through again and again in order, because it's linking 3 times, and you pick up a linking number of 3. You can look at other examples that we're familiar with and see how they look from this point of view. For example, in the Whitehead link, we had the following. That's the way it was. Right, there's the Whitehead link. And you see, looking at the Whitehead link that way, you see immediately, oh yes, the linking number is 0 because there's a piercing up and there's another piercing down. And it adds up to 0. Okay, so it's very important and very flexible to think of linking numbers in terms of the piercing number of one curve with a surface that bounds the other curve. And you're going to have some fun convincing yourself that is also a geometrically invariant, topologically invariant way of thinking about the linking number. What would happen if you chose a different surface? What would happen if you moved the link around a bit? Try some examples and begin to see that this is indeed topological. Our proof was very easy to do when we did Reidemeister moves. Here you should think geometrically and 3-dimensionally and convince yourself that it's working. And we can talk about how do you make that kind of thinking into a proof. But you see, one of the things that's happening here is that it's very useful in understanding the topology of something to ask yourself, does this curve bound something that I can understand? It's very useful to ask that question. And sometimes things bound things and sometimes they don't. Sometimes there's an obstruction to being the boundary of something. But when you're in 3 space and you have a knot, every knot is the boundary of a surface, for example. So here's here's a nice fact that we could end today with. Every knot, okay, is equal to the boundary of S, where S is a surface in 3 space. And S can be orientable. No Mobius bands in it. I'll give you an example and we'll stop there. Suppose you take the trefoil knot. Then we can find a surface by just the checkerboard coloring of the trefoil knot. See, there's a surface. You could look at those checkerboard colorings that we've been doing as surfaces, but some of them are not necessarily oriented. Some of them have Mobius bands in them, but not this one. This one is an orientable surface. If you take a normal vector to it and you move it around, it gets flipped down when you come here, but when you come back through, it gets flipped back up. There's no circuit in there that would take you from normal vector up to normal vector down, as there would be in a Mobius band. A Mobius band is a perfectly nice surface, but it's non-orientable, and non-orientability for us geometrically can be just taken to mean that you choose a normal vector to the surface and move around. And if you move all the way around on a cycle, you see you end up with the normal, you come back to where you started, but the normal vector is flipped. If that happens, you're in a non-orientable surface and you add a Mobius band. Well, there's no Mobius band here. This is an orientable surface S, and the boundary of S is equal to the trefoil knot. But I say that every knot bounds an orientable surface, and there's a very pretty method for creating one. I'll tell you at the beginning of next time. So we'll stop here.